recording. Hello, everyone. We are starting our CMSA Colloquium. Today, we're pleased to have Weinan E. from Princeton University. Professor E works in the area of applied mathematics, machine learning, and mathematical physics. And today, he will talk about machine learning and PDEs. Professor E, take it away.
Okay, thank you. Thank you very much for the invitation. I'll talk about three topics. The last topic is going to be quick. The first topic will be new algorithms for solving high-dimensional PDEs, so PDEs in hundreds and thousands of dimensions. And second is a topic about regularity theory for high-dimensional PDEs. And then I'll talk about PDEs that arise from continuous formulation of machine learning. Okay, let's start with a general remark about what is machine learning. Well, it's just a set of models and algorithms for approximating functions, probability distributions, dynamical systems, and solutions of differential and difference equations. Roughly speaking, supervised learning is about approximating functions. Unsupervised learning is about approximating probability distributions. Recurrent neural networks is about approximating dynamical systems, and reinforcement learning is about approximating solutions of Bellman equations. Now, in this talk, I'll be, most of what I do is related to supervised learning. Now, these set of algorithms, what machine learning distinguishes from traditional algorithms is that these machine learning models are particularly effective in high dimensions. So you can think of neural networks as being the replacement of polynomials in high dimension. So traditional algorithms for doing these approximating functions, dynamical systems, solutions of PDEs are usually based on polynomial or piecewise polynomial approximation of functions. And these don't work very effectively in high dimension. And neural networks are the right replacement of polynomials or piecewise polynomials. So this is a general idea. And I'll make them a little bit more precise in the following. So this is the typical problem that's solved by machine learning, deep learning techniques. It's a classification of images. So here we have a set of images. This particular set of data set is called CFAR10. So we have these images, and they are labeled into 10 categories, depending on what the image contains. For example, these are deer, these are cats and dogs and stuff like that. The task is to learn a function that maps each image into its category. So this is a discrete value function because the value f star only takes 10 values, and it's defined on a high dimensional space because each image can be viewed as a point in a 32 by 32 by 3 dimensional space. 32 by 32, that's the number of pixels of the image, and 3, that's the dimensionality of the color. We have color images. So that's 3072 dimensional space. So we are looking for a function, approximating a function in a 3072 dimensional space. This is a typical example of the kind of issues we deal with in machine learning. Now, the main components for supervised learning. So first of all, what is supervised learning? Supervised learning is the following task. Given a data set, xj and yj, so yj are called the labels, and it's given by the value of an unknown function f star at these points xj. So f star is unknown, it's called the target, is our target function. So given this data set, we are supposed to approximate accurately the unknown target function f star. So this is really a function approximation problem. The well-known DNN, the deep neural network SGD, stochastic gradient descent paradigm for solving this problem is as follows. It's got 3 components. The first component is to construct a hypothesis space, which is just a set of trial functions. We're going to use these kinds of functions to approximate f star. For example, we can choose functions of this form, where AJs, WJs are constant coefficients, And sigma is a nonlinear function called activation function. For example, this is the most popular choice of activation function. It's called a ReLU activation function. So these kinds of functions are two-layer neural networks. Two-layer because we have two sets of coefficients. And we're going to use theta to denote the parameters. So typically, we want to look for optimal parameters, parameter values, such that this function approximates our target function in the best way. So that's the first component. The second component is to formulate an optimization problem with which we're going to find the optimal parameters. Typically, since we are given a finite data set, we just try to fit the data. So this would be a very natural choice. And we can have more general choices of these kinds of loss functions, so-called loss functions, also called empirical risk. And the third component is to solve this optimization problem. And the simplest idea would be this gradient descent algorithm, where eta is the learning rate. So this is the standard gradient descent algorithm. We take the gradient and we move one step. In doing so, at each step, you have to calculate this gradient, which is the sum of n terms, and n is the size of the data set. If we have a large data set, this would be a large sum to calculate. So in practice, we don't do this. In practice, we just randomly pick one term from this sum, from this average, and use that to represent the gradient. And this is the stochastic gradient descent algorithm. So when you're training like the image classification problem, you would randomly pick an image and try to fit the labels of that image at each step. And next step, you would randomly pick another image and do the same thing. So this is a very natural algorithm from the viewpoint of practice. Okay, now, two-layer neural networks. So a very important point is how to choose these functions. This is an example of two-layer neural network. In practice, the most popular or most powerful neural network models seem to be the so-called residual neural network model. The residual neural network model is described by a discrete dynamical system. So we have these ZJs, DKs. These are the values of the state of the dynamical system. We started with X. So X is our independent variable. And then we do this discrete iteration where WK is the parameter. Well, it's a matrix really, but it's the parameter at the case step. And then at the last step, we take a vector and contract ZL, which is also a vector, and form a scalar function. So we're going to use these kinds of functions as the functions in the hypothesis space. So in this case, the WKs and alphas are the parameters to be optimized. And we choose the same kind of loss function. Sometimes we add a regularization term, but oftentimes we don't, and do stochastic gradient descent. And this is the most popular deep neural network model that's used in practice. Keep that in mind. So now let's talk about, I'm going to be talking about how to apply these kinds of ideas to solve PDEs, high dimensional PDEs. The idea started with this paper, which I think was the first paper that used deep learning to solve high dimensional problems in scientific computing. And we chose, at the time, we chose stochastic control as the setup. Now, in stochastic control, we have a dynamical system. Okay, the states are ZL, these are the states, and GL is some given function, and AL is the control at the time step L. And these are noises, white noise. And we want to choose these control to minimize an objective function, standard objective function, where we have the running cost here and the terminal cost here. Now, suppose we look for a feedback control, which means we look for a function, the optimal control as a function of the state. So this is a so-called policy function. And we want to approximate that by some neural network model, never mind which neural network model, in which we denote theta L to be the parameters of the network at step L. Then our task becomes to choose these parameters theta L so that this cost, which is really the cost that we were interesting, is optimized. Now, this problem has a lot of similarity with the ResNet, with the model we just discussed, with this model. And the analog is as follows. This guy is a lot like our ResNet. It's a discrete dynamical system. And this guy is like our loss function. Because the loss function is expressed as an expectation. So you can do the philosophy of SGD applies directly. So that's why actually we choose this stochastic control problem as the first example to illustrate the power of deep learning, because it has a very close analogy with ResNet, ResNet-based deep learning algorithms. You have the ResNet SGD paradigm applies directly. Here is an example of the application. It's an example that we cooked up. It's an energy storage problem with multiple devices. N is the number of devices. This is a rather high dimensional problem that were definitely not accessible from using the classical algorithms. And you can see, as training goes on, the solution converges nicely, where the shaded area is the error bar when you choose different initialization in the training. And there are ways to check whether these answers are accurate, but I'm not going to go through them. Second example is solving nonlinear parabolic PDE. So let's take this nonlinear parabolic PDE. I formulated it as a terminal value problem, not an initial value problem. So this has the wrong sign. But as a terminal value problem, this is the right sign. Our goal, say, is to calculate the solution at initial time. So it doesn't have to be initial time, anytime before t. Before t. In order to formulate machine learning algorithms, we first try to reformulate this problem as a stochastic optimization problem, just like before. So in this thing, we ended up with a stochastic optimization problem. Stochastic optimization, because the objective function is an expectation. So here, for this nonlinear PDE, we want to do the same thing. We want to write this as a stochastic optimization problem. And this can be done by with the help of backward stochastic differential equations, which is a very important notion and introduced in this very classical paper. So the equivalent formulation is as follows. We consider this optimization problem where xt is defined by this process and yt is defined by this process. And then we match the terminal values between the given terminal condition and the value of yt. And one can show that these two problems are equivalent in the following sense, namely taking a solution of this PDE, then the value of that PDE along xt gives the process yt, the value of the process yt, and the gradient is the process zt. So this is an equivalent formulation. Now, given this equivalent formulation, you see that it's very much like the control problem. The control problem, we minimize this thing subject to this dynamical system. So this dynamical system acts like a constraint. And here we minimize this thing subject to this dynamical system, which acts as a constraint. So we can do this similar thing, very similar things. First, we're discretizing time, and then we parameterize this initial value, and also the process z, which acts like the control here, as using neural networks, and then we just choose the optimal parameters in this neural networks to minimize the mismatch between the value constructed using the process and the terminal value that's given. So this algorithm is called deep BSDE method. It was the first method, deep learning based algorithm for solving high dimensional PDEs. And then let's consider some examples. For example, let's think about this simple control problem. It's called linear quadratic Gaussian control, where lambda is a parameter. This is the Weinan process. Wt is the Weinan process, and m is the control at time step at time t. And we choose the control in order to minimize this cost function. Again, the terminal cost, the running cost. The solution of this PDE problem, that value function of this stochastic control problem, solves the Hamilton-Jacobi-Bellman equation, which is this guy. And then when one can write down, again, it's a terminal value problem. One can apply the well-known Hopf-Kohl transformation to this problem, and then write down the exact solution, which is this. So then you can use this exact solution to calibrate the accuracy of the deep BSD method. And that's shown here, the solution at this particular value as a function of parameter lambda. So you can see that the two agrees pretty well. Here's another example which turned out to be the most popular application right now for the deep BSD method, which is some version of Black-Scholes equation. Here we consider Black-Scholes equation with default risk so that the equation becomes nonlinear. This particular version, particular model for modeling default risk is taken from this paper. Also a classical paper by Tafi. And they solved, in this paper, solved this kind of a PDE for dimension 5. By the way, this is a cubic nonlinearity, which I didn't write down. And here we solve this PDE for dimension 100. And you can see it converges pretty well. And incidentally, we also developed another algorithm called multi-level Picard iteration. And that algorithm has been shown to converge with certain accuracy, and we use that algorithm to calibrate the accuracy of the BSD method. So this, as I mentioned briefly, that it's being applied to pricing all kinds of exotic options, basket options, interest rate dependent options, all these exotic options. Right now, that's where the BSD method has been applied the most. Okay, so the fact that we can solve these high dimensional PDEs, 100, I showed how to solve 100 dimensional PDEs, but you can solve 1,000 dimensional PDEs also. The fact that we can do this means that the solutions of these PDEs have low complexity in some sense, even though they're functions in high dimension. The question is, how do we characterize this low complexity? Well, the intuitive answer is that, well, they can be approximated easily. Again, is how to quantify this. So let's go back to the classical viewpoint. Classically, we calculate, we have a sort of a three-step procedure. We talk about approximation theory, and then we talk about regularity. Approximation theory requires some regularity concepts. And then we talk about regularity theory for PDEs. And then we talk about numerical algorithms for solving these PDEs. So classically, we have the three-step procedure. The first step is approximation theory. And here, it turns out that regularity is a measure of the complexity, how easy it is to approximate a particular function using simple functions like piecewise polynomials. For example, let VH be the space of continuous piecewise polynomials of degree k over a regular grid of size h. Then we have this little theorem, almost like a theorem. It should be put in quotation marks. Namely, the minimum error, the best one can do for a certain target function is bounded by h to the alpha, where alpha is the regularity of the function, sublevel regularity of the function. This is the sublevel space of order alpha. So, so the bigger the values of alpha, the faster the convergence rate, the easier it is to approximate U star. So this is the this is a classical approximation theory, namely the order of accuracy in such an approximation scheme depends on how many derivatives the target function has. So now, knowing that, so the next thing when it comes to approximating solutions of PDE is to ask how regular is the solution of that particular PDE, namely whether the solution belongs to some sublevel class or similar spaces. So that would be the regularity theory of PDEs. And then classical numerical analysis is about showing that a particular algorithm, finite difference, finite elements, converges with certain order of accuracy. So this is the classical framework. Now, an important limitation for the classical framework, if we go back to here, is that if we want error to be less than epsilon, if we want to reduce the error by a factor of epsilon, then we have to increase m, the number of parameters. So m is the total degrees of freedom in this approximation scheme. So we have to increase m by epsilon to the minus d over alpha. So if epsilon is 0.1, then this means we have to increase m by 10 to the d if alpha is equal to 1. So think about d equal to 3072. This will be a huge number. So this is the problem with all classical approximation schemes, namely there's a curse of dimensionality. As the dimensionality goes up, the complexity, the number of free parameters required goes up exponentially fast. That's bad. And it's not just that. It's not just these classical algorithms like finite difference, finite elements that are not good enough for high dimensions. There are increasing evidence that these notions of Sobolev or Bessel spaces, regularity-based spaces, are not a good measure of the complexity of functions in high dimension. These function classes are just too large. The difference between C1 and C2 in high dimension is not that big. Okay, now this is exactly where machine learning can help, as I sort of try to suggest. So in a machine learning scheme, we need to develop a different kind of regularity theory. So we need a new approximation theory. We need a new regularity theory for high dimensional PDEs. So by new approximation theory, I mean theorems of this type, where these HMs are not piecewise polynomials, there are neural networks, say. And we want approximation schemes for which the convergence rate, alpha, does not depend on dimension. So m, again, is the number of free parameters, the degrees of freedom. So we want approximation theorems that says that, well, this holds if and only if some norm, some measure of the target function is finite. So this would be like a Sobolev norm in this, the replacement of Sobolev norm. Question is, can this be true? And then if this is true, then the regularity theory becomes the following question, namely for solutions to a particular PDE, do these Sobolev-like norms, the new norms, are they finite for the solutions of the PDE? So we're going to address these questions. So first of all, what is the value of alpha? What should be the value of alpha that we can expect? Well, alpha is half. And the reason is the following. We just think about this computing integrals or computing expectations, then Monte Carlo approximation of the integral gives the following error identity. So this is the Monte Carlo approximation, xj, IID samples of the probability distribution mu. Then we have this identity here. And you see that, well, the exponent does not depend on dimension. There's no 1 over d here. And this is like our gamma. This is like our gamma of alpha. So if you compare these two, you see that alpha should be half. It's 1 because there's a square here. So alpha should be half because we can't expect function approximation to have a better rate than Monte Carlo. If you have a better rate here, we can do a different, improve this integration scheme. So therefore, the best we can hope for is the analog of this, which will be this. And this plays the role of variance. So different Monte Carlo schemes differ in how big the variance are. So different neural network approximation schemes differ in how big these, pseudo norms, these norms are, how big these norms are. So let's look at how to implement the scheme, whether this is possible. start with a simple linear model called random feature model. So here we have a collection of feature functions. So a feature function is a function of x with, depending on a parameter, which is a random variable w, and pi is the probability distribution of the random variable w. So by random feature model, we mean the following. Let's pick an IID realization of the distribution pi. Just pick m, IID samples of the distribution pi, and form this hypothesis space, linear combinations of these random features. And this is going to be our hypothesis space. The unknown parameters are just these coefficients aj. So this is the linear space. And then we define this funny norm. And the norm is defined as follows. Let's consider functions of this type, which are almost like continuous analog of these guys. So consider function of this type. And then if a function admits this representation, this kind of representation, we can define its FP norm by the piece moments, like the piece moments of the coefficient A. And if P equal to 2, this is exactly the so-called reproducing kernel Hilbert space with the kernel defined by the random features. So FP is like the LP extension of the associated reproducing kernel Hilbert space. Now, why we define these funny norms? Well, we define these funny norms because they are the ones that that goes into the direct and inverse approximation theorem. So the direct theorem says the following. So these are easy theorems to prove. Actually, there might be in the literature. It's just not clear which, where it's in, where it is. But I don't think these are new. So assume that L infinity, F infinity norm of the target function is finite. Then for any number delta between 0 and 1, with the probability at least 1 minus delta over the random samples of these features, vectors, there exists a coefficient such that the random feature model approximates, with that coefficient, approximates the target function with the desired convergence rate, namely 1 over m with some coefficient gamma. So this would be our gamma in this case. Conversely, if a target function can be approximated by random feature models with bounded coefficients, then this function must have finite F infinity norm and must admit this representation, and the F infinity norm must be finite. So these are easy theorems to prove, and they're the analog of Jackson and Bernstein theorems in classical approximation theory. Okay, so now let's consider a more realistic model, well, a more neural network kind of a model, namely two-layer neural network models. So I have these two-layer neural network models. The difference between what I wrote before and what I write here is that I put in a 1 over m factor here. But this doesn't change anything because these coefficients are arbitrary. I can absorb the factor into here. But writing it in this form suggests that we're going to consider functions that emit this representation, where rho is a probability distribution in the parameter space of A and W. So again, this means that the function can be expressed as an expectation. So this will be the analog of this representation here. Now, for functions that can be represented in this form, let's define what is called the Barron norm, which is defined as follows. We take this mixed second moments or fourth moments, I don't know how to call it, and then take the square root. And this we call this Barron norm. Actually, it's kind of confusing because Barron defined a different norm. It's not the same as this, but we decided to call it Barron norm. And here we have to take an infimum over all probability distributions for which this is true, this holds. And the Barron space, Barron functions are defined to be continuous functions whose Barron norm is finite. Okay, now an immediate question is what kind of functions are Barron functions? Namely, admit this representation with a finite Barron norm. Oh boy, I need to speed up. Well, here's a theorem proved by Barron and Klosowski. Namely, if this norm, this is a norm defined by Barron, where f hat is the Fourier transform of f. If this norm is finite, then f is a Barron function. And it admits this kind of representation. And the Barron norm is bounded by this Barron norm, which we call, in order to make a difference between this kind of Barron norm and this kind of Barron norm, we decided to call this Barron's spectral norm. Now, this Barron norm, Barron's spectral norm is kind of a little bit of unsatisfactory in the sense that this condition depends on dimensionality. Whether, the condition that this quantity is finite depends on dimensionality because, integrability. Now you might ask, well, what kind of functions are Barron functions? Is there anything we can say more about it? This, this theorem is a general theorem, but it's not very intuitive. So the following is a structural theorem for singular sets of Barron functions. So first of all, Barron functions are Lipschitz. It's easy to check. Oh, by the way, here I'm considering activation functions, which is a ReLU activation function. I'm thinking about that case only. So in that case, it's easy to see that Barron functions are Lipschitz functions, and the set on which a Lipschitz function fails to be C1 is called a singular set. And it can be shown that the singular set of Barron functions, the Barron function have the following structure. Namely, it can be decomposed as a countable sum of functions whose singular sets are affine subspaces. So as an immediate application, one can show that if you take the distance to the unit sphere, that function is not Barron function because its singular set is not a countable union of affine subspaces. Now this guy, distance to the origin, is a Barron function, and that's easy to check. So for these, so now for two-layer neural networks, we can also prove direct and inverse approximation theorems, which are very much the same as before. But these are for Barron functions, for the two-layer neural networks and Barron functions. And similar kinds of approximation theory can be developed for ResNets, residual neural networks, in which case we introduced something we call flow-induced space. So that would be the analog of Barron space or reproducing kernel Hilbert space. And for multi-layer neural networks, we also introduced something called multi-layer space. Again, plays the role of Barron functions and stuff. And and these kind of theorems can be proved. Although in this case, the M is not exactly M here. There is some exponent that depends on the number of layers. So now, the very natural question is, can we establish a regularity theory for these kinds of spaces, for these kinds of new function spaces? For example, what about regularity theory of PDEs in reproducing kernel Hilbert space? You can see reproducing kernel Hilbert space is the simplest example of the new kinds of function spaces introduced here. Well, there are very few results of this type. I'm going to report results with my postdoc, Wojtowski. There's another paper, interesting paper written by Jianfeng Liu in Duke University and his collaborators, which consider regularity theory for Barron's spectral space. If you remember the Barron's spectral space, which we defined with the help of Fourier transform. So now I'm talking about Barron space and multi-layer spaces. So first consider this Poisson-like, elliptic equation with constant coefficient. If we consider Poisson equation like this form, then the solution grows like x to the cube. And you can show these kinds of functions cannot be Barron. So on an infinite space, whole space, we cannot do this kind of regularity theory with the Laplace operator. But if we add a screening effect, if we add this term, then there's a screening effect, then we can show the solution satisfies this estimate. So if the right-hand side is Barron, then the solution is also Barron. And for heat equation, you can write down the solution, and then you can check, pretty straightforward to check that, if we view it as a function of x and square root of t, then we can, if we view it as these as independent variables, then we have this estimate. And if we view it as a function of x only, with t as parameters, then we have this estimate, where you have coefficient that depend on square root of t. And if you look at the homogeneous part, the solution, the inhomogeneous part, namely we put the right-hand side f here. We'll put it right. By the way, there should be f to begin with. This is a mistake. There should be an f. If we look at the solution with the initial condition 0, then that part of the solution satisfies this kind of a Barron estimate. These can be proved by straightforward formulas. Just check the formulas. Now, this is a little bit more interesting. Let's look at this Hamilton-Jacobi equation. Then by the Hopf transformation, one can reduce this problem to a heat equation. And that helps. And then again, we can prove these kind of estimates, namely the solution. We don't know whether, if the initial condition is Barron, we don't know whether the solution is Barron, but we can prove that the solution is in the 3-layer space with this kind of estimate. So this means that, well, we don't know whether the solution can be approximated by 2-layer neural networks, but we know the solution can be well approximated by 3-layer neural networks. So let's consider a problem in a bounded domain. Here is a very simple example with Laplace's equation with this boundary condition with its ReLU. And then you can show that the equator is part of the singular set. But the central plane is not the singular set. So this means that the singular set is not a of the solution, cannot be a countable union of affine subspaces. So therefore, if dimensionality is bigger than 2, it's not a Barron function. Okay, so summarize, these are the simple observations. For translation invariant linear PDEs, solutions often lie in Barron space. Boundary values break translation invariance. Now, even harmonic functions with ReLU boundary values are not in Barron space. Well, it's not known whether they're in 3-layer or more layer spaces. And nonlinear PDEs might need deeper neural networks to approximate, as we saw in the viscous Hamilton-Jacobi equation. So what about solving? So I've said a lot about solving high-dimensional PDEs. What about solving low-dimensional PDEs? There's also a lot of talk about solving low-dimensional PDEs, like 3-dimensional Navier-Stokes equation, using neural network models. So here, I think the situation is very confusing. I think there's a lot of confusion. Well, to begin with, there are some advantages of neural network-based algorithms. It's meshless. There's no grid. One doesn't have to put up a grid. It's naturally adaptive. You can put more. Naturally put more grid. There'll be higher resolution in places where the solution tend to be singular. And the most important of all, I think this is actually overrides these two, is that it's easy to write codes because there's lots of Python libraries. It's just a feature with the fact that people have developed a lot of tools for Python. There are also very distinctive disadvantages. For example, it's low order accuracy, half order accuracy at most, and it's difficult to optimize. These are non-trivial disadvantages. And there are also, let me also clarify some terminology. Consider this simple PDE. Now we have in numerical analysis, we have 3 kinds of formulations. a rich formulation, which is to formulate this as a variational problem. This is an equivalent variational problem. Colloquium formulation, which is this kind of a weak formulation with test functions. So V is a test function, and U is a trial function. And least square formulation, which is to do this, just take the square and solving this minimization problem. So corresponding to these different formulations, there are different algorithms. So in classical PDE, we prefer this to this, and we prefer this to this. So there is a deep risk algorithm developed by my student and myself, which is the direct extension of this. We won't just replace this by some neural network models. And actually, we did it because we want to develop some sort of a Colloquium formulation. We still don't know how to do that. Unfortunately, deep Colloquium method, the terminology deep Colloquium method is being used for this formulation, which should be least square formulation. But they decided to name it deep Colloquium method. So I would say deep Colloquium method, a real deep Colloquium method still doesn't exist. There's some attempts. There's a paper by Gambao and his student, which made an attempt, but I don't know whether that qualifies as a deep Colloquium method, because at the end of the day, they still make that into a variational problem, not something of this type, where it involves test functions and trial functions. And there's also something very popular, something called physics-informed neural networks, which is the same thing as this. It's a deep, it's really least square formulation. Okay, anyway, this is the state of the art, and I would say it's highly unclear whether there is a real advantage besides the fact that it's easy to write codes for using neural network models to solve these kinds of low-dimensional PDEs. But I'm ready to be convinced otherwise. I'm happy to be convinced otherwise. So in the rest of the 10 minutes, I want to discuss PDE formulation of machine learning. How do we formulate machine learning as a PDE problem, as a well-posed PDE problem, continuous formulation of PDEs? So let's say, well, we want to minimize this risk, this so-called population risk. This is our objective, that's clear. We want to cook up some models, some versions of this guy that contain some parameters, and then minimize the difference between this and our target function. This is our objective. And the question is, how do we represent this? Well, one example is to represent that we saw before, is to represent the trial functions in this form. And this can be expressed as an expectation, and that's very important. So in here, we can say that, well, pi is fixed and a is the only parameter. Or we can say both a and pi are parameter. Or we can say that a is fixed and pi is the parameter. So whichever way is fine. So this would be a variational problem once we decide which is going to be regarded as being the parameter. And then we can solve by GD or SGD. No, well, first we have to discretize in the data space, because we don't know how to calculate this expectation. We have to approximate this population risk by empirical risk, because we only know a finite set of training sample. But after we've done that, we can just solve this problem using GD or SGD or other optimization algorithm. And this is just a variational problem. And then we need to discretize, of course, but I'll talk about discretization later. Now, as you see here, a very important component is how to represent this function. And this is the one representation. And we can have other representations. We can have a more general representation where we regard A as being as a free parameter, instead of a function of W. We can lift the parameters to a higher dimension, consider both A and W as being the parameters. And then their distribution rho is going to be the parameter theta, for example. Or we can consider more general feature functions, not just feature function of this form, which is neural network type. We don't have to consider neural network type of feature functions. We consider this guy. This is the one way to represent functions, and we call this integral transform based. Another way to represent functions is to consider dynamical systems of some form, and then the flow map of the dynamical system or the time one map after some contraction gives us the trial function. So in this formulation, we need to decide how to represent right-hand side. Well, we can take these representations and use that to represent right-hand side. So now the difference is that the parameters becomes with these one-dimensional families of functions or one-dimensional families of probability distributions. But this, at the end of the day, this is another form to represent these trial functions. Okay, so once we've decided how to do this, so we have the variational problem to solve, and then we just solve by some variational optimization algorithm. That's one way to do it. Another way to do it is to first formulate the optimization algorithm as a continuous PDE. For example, we can write down some gradient flow for this kind of a representation where A or pi is going to be the parameter. If we regard A as being the parameter, we can do some model A dynamics. This is a terminology that's adapted from statistical physics. This is called model A dynamics, straightforward gradient descent, gradient flow. And if we regard pi as being a parameter, we cannot do this because this would not, pi is a probability distribution, so it needs to be non-negative and needs to, its total integral has to be 1. So we have to use model B, which is the following recipe. We first calculate the so-called chemical potential, and then we use the Fick's law, and then we use the continuity equation. So this is the model B gradient flow. It can be shown that as long as the solution is smooth, pi stays being a probability distribution. And this is also the gradient flow under the Wasserstein metric. Anyway, we'll get these kinds of PDEs, really integral differential equations. So then we just have to discretize these PDEs. This becomes a standard problem in numerical analysis. How do we discretize? Well, we discretize population risk into empirical risk using training data. That's easy. The expectation becomes sum, a finite sum. And then to discretize the gradient flow, this equation or this equation, we can use, finite difference, finite element, or spectral method. These are not bad in low dimension. But in high dimension, we need to use the particle method, because particle method, so these guys don't work in high dimension, as we already mentioned. Particle method is the only one that works in high dimension. It's the dynamic version of Monte Carlo. Or we can use smooth particle method. Anyway, so these guys are the ones that are preferred in high dimension. So let's look at how that works out in practice. So let's consider this representation of the trial function. And our parameter is the probability distribution rho for the parameters, for these parameters. And the gradient flow looks like this, where V is the usual variational gradient. This equation happens to be the same as the so-called mean field training, a mean field limit of two-layer neural network models. There are a number of very nice papers that discuss the mean field limit of the gradient descent dynamics for two-layer neural networks, and this is exactly the mean field equation they derived. But as you can see, it can also be motivated in a very natural way. Now, if we discretize using a particle method, namely we replace this probability distribution by a finite sum, and let's call these guys particles and call them uj, then it can be shown that this equation is exactly equivalent at this equation, and this equation is nothing but the gradient descent flow for the loss function which is exactly the loss function here, but restricted to functions, to rows of this kind. If you plug in rho equal to this, and then you calculate the loss function, then it's this I loss function here. So this PDE is exactly the same, is exactly equivalent to this gradient flow dynamics of a finite number of particles. And these finite number of particles are actually the weights for the neural network, for a two-layer neural network. So what we are saying here is that this continuous looking equation is actually contains embedded in this continuous looking equation is the discrete gradient flow of a two-layer neural network model, except that it's scaled. Usually in two-layer neural network, we don't have this 1 over m. Now we have this 1 over m. So it's a scaled two-layer neural network. Okay. I don't have time to describe this. So there, the one question is what about the convergence of these gradient flows? Well, unfortunately, even though this is a nice Wasserstein gradient flow, the functional here is not displacement convex, which means the usual theory doesn't apply. And as a matter of fact, we're almost back to step 0. There's one result, interesting result, which is proved by Gisèle Bach, and also improved by Wojtowski, which essentially says the following: that as long as the initial condition, the initial distribution has full support, then if there is convergence, if this thing converges, it must converge to a global minimum. So we don't know whether it converges, but if it does converge, then it converges to a global minimum. Now, this theorem, there are lots of technical issues with associated with this theorem that I'm going to skip. But this is almost the only result that we know, namely that if there is convergence, then it has to converge to a global minimum. There are some other simple example results which I'm going to skip. Okay, let me end with a discussion about flow-induced representation. Remember this? We use a flow and then the time 1 map. I should move this to here, really. I should move this to here. Now, from the flow, we'll construct this a trial function, and then we choose the controls, which are this one parameter family of probability distributions to minimize the population risk. So this is a control problem, where the controls are these one parameter family of probability distributions. In control theory, a very powerful tool is contracted as the maximum principle. So this is the contracted maximum principle restated. We define the Hamiltonian over this state, co-state, and parameter space. Now the parameter space is the space of probability distributions with finite second moment. And we define this Hamiltonian. Then contracted maximum principle says that the optimizer has to be Argmax of the expected Hamiltonian for each pseudo time tau. So for each pseudo time tau here, this has to be true. And then the states and co-states satisfies the forward and backward equations, Hamiltonian system with boundary conditions, with initial and boundary terminal conditions. So this is the standard contracted maximum principle. Now, if we want to formulate a gradient flow, we just have to replace this condition by the gradient flow, which is this guy. In this case, we have a one parameter family of gradient flow. Now, the next thing is, so this will be our PDE kind of a formulation of gradient flows in this situation. Now, if we discretize these guys using the simplest algorithms, namely forward and backward Euler here, and then particle method here, then you see that we cover the gradient descent dynamics with backward, forward and backward propagation for the scaled ResNet. So it's not the usual ResNet, it's a scaled ResNet. So in that sense, it's also quite nice. Namely, we show that these gradient flow, these popular neural network models arise very naturally from a continuous formulation. Now, we don't have to use the gradient flow. We can just formulate some algorithms based on contracting maximum principle directly. That can be done, and it's done in this paper. It turned out, if you just do it directly, the performance is pretty poor. And we ended up formulating formulating the maximum principle on an extended space with some auxiliary variables B and Q. By the way, this rho should be, I should write as lambda. This is some sort of extended Hamiltonian with a penalty, some penalty terms. Well, the details here is not so important. Yeah, not important at all. You can look at the paper if you're interested. The point being that maximum principle can be used as a starting point to formulate training algorithms, and the performance is not so bad. You can see in this case where we have some bad initialization, it actually performs much better. You know, it converges much faster than the standard SGD type of algorithms. Although the walk clock is not that dramatic because we didn't optimize the optimization at these time steps. So these, you know, maximum principle does this, gradient flow does this. Okay, so summarize. What have we really learned from machine learning? So I think there is lots of tricks in machine learning. There are these stochastic GD, SGD, there are these neural network models, there are these batch normalization. There's lots of tricks and lots of techniques. But I think the most essential, most important point of all is how to represent functions as expectations. So how do we develop representations of this type? So this is a simple expectation representation. And this is a little bit more complicated. We consider this dynamical system whose right-hand side is an expectation. And then we do a contraction to get a function. So these kinds of things, these kind of expectation representation can be used as starting point to develop machine learning algorithms, continuous formulations of machine learning. And then we can use particle method, spectral, or other numerical methods to discretize these guys. And this, to me, seemed to be a more intrinsic formulation of machine learning. If you come up with some other representation, and then that would be a starting point of an entirely new class of machine learning algorithms. Incidentally, I didn't explain this. This happened to be the representation that produces multi-layer neural network models. Okay, I'll end my talk here, and I'll be happy to take some questions. Oh boy, time's up.
Thank you very much, Professor E. Let's see if we have questions. I see a question in the chat. Okay, if anybody from the audience has a question, please go ahead, just unmute yourself and ask. In the meantime, in your slides you had, you did show your error bands, and you mentioned that you derive them by just using different starting values. This approach can be super expensive and also potentially biased. Do you have any thoughts about how to really optimally obtain error bands?
I can't hear you very clearly. Somehow it's kind of broken.
Oh, I'm sorry. Okay, let me.
Now it's better, yeah.
Let me repeat. It's a basic question is how to. What would be the optimal way of obtaining confidence bands for your estimates?
What would be the optimal way to obtain what?
Error bands, confidence intervals for your estimates.
Oh, okay. No, I've never thought about it. Confidence intervals.
You basically, when you did show error bands in one of your first slides.
No,
And you said that you obtain them by just trying different. But that method, for example, can be super expensive for complex
usually
models.
usually the theorems look like this. You know, with the probability 1 minus delta, this is true. But if you want confidence intervals, well, confidence intervals. Well, that's like already some sort of confidence interval, isn't it? That we have with the confidence, you know, we have this. Yeah, this looks to me like already some sort of confidence interval. Although you can see this is, you know, some L2 norm and yeah, if you have, you know, LP norm, this will be different.
Okay. Are there other questions from the audience? People are thinking. You mentioned that in some cases you actually want even 2 layers is not enough.
Yeah.
You want 3 or more. But theoretical argument that in principle, even 1 layer, which is very wide, should be enough for function approximation. So what is your argument that you actually want more than 1 layer?
So for example, in this theorem here, we cannot show. We suspect that if you replace this by Barron norm, this wouldn't work. This wouldn't be true, which implies that the solution cannot be very easily approximated by a 2-layer neural network. This W3 stands for the 3-layer space. So this says that it can be efficiently approximated by a 3-layer neural network. But most likely it cannot be efficiently approximated by a 2-layer neural network. That's what these kinds of estimates say. Implies.
And by efficiency, you mean?
That with these kinds of error convergence rates, these kind of convergence rates.
Yeah, the convergence rates. Okay, fair enough. Yeah, that's a familiar argument that just with more layers, it's easier to optimize those networks. Yeah. Okay, there is a question from Ying Wu.
Hi, Professor Yi. I just first want to confirm if you mainly consider the convolutional neural network.
Actually, I didn't consider convolutional neural at all. I considered fully connected neural network. Convolutional neural network requires a different theory.
Oh, well, right. Okay.
It requires, you know, it's in the same spirit, but different spaces and then different considerations.
Yeah, that's actually my question. Thank you so much for your confirmation. So I was actually meant to ask how other neural networks such as convolutional or reticulate or other sorts of deep neural network may perform. Do you have any insight?
Convolutional neural network, that's a good question. Yeah, so there is some, you know, I think we have some ideas, but there's still an important gap in constructing the right theory for convolutional neural networks, because convolutional neural networks works much more effectively for translation invariant functions. So we need to consider translation invariant functions, and we need to have some extra factor, in boost in the rate or improved estimate. And so far, we haven't quite got that. And what is the other neural network you mentioned?
Yeah, I was thinking reticulate RNN and CNN and then maybe even, I don't know, reinforcement learning, because you do have loss function and the trade-off.
Okay, so for RNN is not about, it's not about learning functions, it's about learning dynamic systems. So we have some papers about our RNN where there's, cursive memory effects we show. Reinforcement learning, actually, it's only the beginning. People are just starting to think about theoretical issues in reinforcement learning with functional approximation. So there's lots of theory about reinforcement learning, but it's all about finite states, finite action space. So tabular case. With functional approximation, namely, use deep neural networks to do these value functions or policy functions. There are like a couple of results very recently, and for linear models, so it's not complete at all. There's an extra complication there, which makes things a little bit, well, a lot harder, it seems.
I see. Thank you so much.
Weinan, thanks. Beautiful talk. I wondered, you gave precise approximation theorems for functions. Do you have approximation theorems for flows?
Yes.
Yeah.
The flow. Which flow?
Well, let's say I have some semi-group of diffeomorphisms. I know something about it. What governs the number of parameters? How should I describe it? How many parameters do I need?
You want to approximate a flow.
Yeah.
You want to approximate a flow. I don't know whether, okay, I'm thinking whether one can translate these theorems directly to approximating flows. So there are two ways to think about, first of all, I don't know. The answer is I don't know. And there are two ways to think about it. One is to translate these theorems I described to flows. And the other way is to think about like the recurrent neural network. So that's also for flows. No, I think it's a good question. That's a good question. I haven't thought about it, not very much.
Hi, Professor. This is Louis Fan. I have a question about your stochastic control formulation for the parabolic nonlinear PDE, where you used backward SDE to formulate a solution of that problem. And then, so how much, I wonder how much advantage is gained using this control approach in terms of numerical computation. I suspect that in high dimension, it's also take a lot of time to simulate this this SDE, or is it not to solve this controlled SDE?
Well, obviously you can make this very hard, right? You can go to very high dimensions, and then it'll be hard.
Yeah.
When you say advantage, meaning advantage over other formulations. For example, we can just do the least square formulation. Take the square and minimize. That's it, right? That's one way to do it. I think it's much easier than that formulation.
Square formulation. I see.
Yeah, certainly much easier than that formulation. For example, that requires second-order derivative, calculated second-order derivative.
So in practice, which one is more? Do people really use the second formulation, this formulate a stochastic optimization problem to solve this kind of PDEs?
In terms of performance, I would say this is better. In terms of performance.
Accuracy.
But this requires you to think about these stochastic PDEs and even backward stochastic PDEs. And sometimes people just don't want to think about it. And do the square and then put that into Python. And that's sometimes people just prefer
Okay.
doing that, and that's fine too. It's not like you can also use that to solve problems. It's not like it's impossible. It's possible. So
Okay.
it's a difference between how much you want to think versus, or yeah.
Okay. Right. Interesting. Yeah. Thank you.
Okay, good. You're welcome.
So this is nonlinearity come from this function f there, right? Is there other kind of nonlinearity that's being treated by this method in practice?
Well, I think it's difficult to put graded f here.
Yeah. Yeah.
Although it's possible. Actually, there's a new paper which deal with that. Actually, there's a new paper that deals with fully nonlinear situation. So I would say this is pretty general.
Mm-hmm. Yeah. Yeah.
Okay, it looks like we do not have any more questions. Thank you very much. It was a great talk.
Well, thank you for your attention.
Thank you. We learned a lot. Bye-bye.
Okay, bye-bye.